Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on February 26, 2026, just yesterday. It addresses the lack of a principled framework for world models by proposing the Trinity of consistency, and it validates this approach with a new benchmark where frontier models like VO3 achieve over 70% success on physical interaction tasks. The paper is titled, "The Trinity of Consistency as a Defining Principle for General World Models." And, as we'll see later, the roadmap it establishes for moving from statistical imitation to robust physical reasoning is very promising. And for those interested in the implementation, the authors have shared their code on GitHub. So Figure 1 visualizes the central thesis, the trinity of consistency required for a general world model, using a Shiba Inu as a running example. On the top left, modal consistency handles the semantic interface, aligning text, audio, and visual data so the description matches the image. Moving to the top right, spatial consistency establishes the geometric basis, ensuring the model respects 3D structures and perspective rather than just painting pixels. Finally, at the bottom, temporal consistency serves as the causal engine, requiring the model to maintain logical continuity across time sequences. Now, Figure 2 applies this framework to evaluate leading models like Sora, Kling, and GPT Image 1.5. The bar charts break down performance across the three pillars: modal, spatial, and temporal consistency, labeled simply as M, S, and T. The top row displays scores for these individual dimensions, showing relatively high performance for spatial and modal tasks. In contrast, the temporal group on the right reveals more struggle, with baseline models dropping below 50%. This confirms that maintaining causal logic over time remains significantly harder than just aligning text with static images. Table 1 provides a comprehensive reference for the mathematical symbols used in the framework. What stands out here is the convergence of vocabulary from distinct fields. On the left, the table lists reinforcement learning terms like policy and trajectory, alongside generative concepts such as latent world state. Meanwhile, the right column introduces explicit physics and geometry notation, including 3D Gaussian primitives and force vectors, which underscores the paper's goal to merge statistical learning with objective physical laws. So, Figure 6 illustrates the architectural evolution necessary to achieve true consistency. On the left, dual tower alignment keeps text and vision on separate isolated pillars, interacting only at the very end. Moving to the center, adapter fusion builds a bridge between these towers, using lightweight connectors to align features without retraining the whole model. Finally, the right side presents the native unified model. Here, the boundaries dissolve completely into a single architecture, often implemented as a multimodal diffusion transformer, which allows deep, joint processing of all modalities from the start. Figure 8 details the multimodal diffusion transformer, or MMDIT, which serves as a blueprint for resolving gradient conflicts in unified architectures. Instead of merging everything instantly, the diagram shows text tokens on the left and visual latent patches on the right, maintaining separate processing paths. Crucially, these modalities only interact inside the central mixing mechanism through a joint attention layer. This separation allows for orthogonal decoupling, meaning the model updates its understanding of text and images independently without one interfering with the other. Because of this structure, the system can improve at complex text reasoning and visual generation simultaneously, which significantly reduces the conflict rate during training. Table 3 now tracks the empirical evolution of video generation across 4 key paradigms. The top row shows temporal inflation models like AnimateDiff, which struggle with consistency, posting a causal reasoning success rate of less than 10%. Moving down to world model priors like Google VO3, we see a dramatic shift in capability. VO3 reaches over 70% on causal tasks and minimizes artifacts, indicated by a frequency fidelity penalty below 0.3. This confirms that integrating physical priors is essential for robust simulation. Wrapping up, the central insight here is that general world models must transcend simple statistical imitation by strictly adhering to the trinity of consistency: modal alignment, spatial geometry, and temporal causality. This shift charts a critical pathway for transforming video generators into physically grounded simulators. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.